So what I want to get at now are the main factors that affect solubility, right? We talked about how solutions form and all about the intermolecular forces. Okay, so you got to have intermolecular forces that are compatible for things to work. Um, what we're talking about with factors that affect solubility is kind of like detail. So once you have a solution, what makes something more or less soluble in it? And the two main things we're going to think about here are temperature and pressure. Okay, and these are going to work for different things in different ways. Okay, so when we think about temperature, there are two big things to work out here. Solids tend to be more soluble at a higher temperature. Okay, so we kind of talked about this when we talked about making a supersaturated solution, right? You want to make some rock candy, so you boil water and you boil a sugar solution, and then you cool it very, very, very carefully, and it can be at room temperature. It's more solids dissolve at the higher temperature. Okay, that's not to say that everything has a higher solubility at a higher temperature. Here we're looking at in this graph. Notice glucose gets way higher as you go. Sodium nitrate gets a lot higher. Sodium acetate gets higher solubility as you heat it up. But then there's some things here. What is the cerium sulfate decreases the solubility. Another good one that I always think about because it happens when I have to deal with the stuff in the lab is chromium phosphate, chromium 3 phosphate. Okay. And that's a problem because you have to boil it in the water to get it to precipitate out, which is really weird. Okay. But it happens. I don't care if you know what things are, just think in general, solids are more soluble at higher temperatures, and don't worry about weird exception things. I'm not going to ask you specifics. Okay. Just kind of general things. The other side of this is gases become less soluble at higher temperatures, right? So if you make a hot Dr. Pepper, it's going to be flat because the carbon dioxide boils out of the solution into the atmosphere because you've heated it up because it's less soluble when it's at a higher temperature. Okay. It's also a problem if you leave cans of soda in your car in the summer when it gets hot, because if it gets hot enough in there, the CO2 that's in the soda will come out of solution and pressurize the can even more, and it could even blow the can open. Okay, so just things we have to pay attention to. The other thing is pressure. And as you might guess, this is not super important for liquids or solids because they're not very pressure dependent in general. What is pressure dependent are the gases, and gases have a higher solubility at a higher pressure. Okay, this was studied by a guy named Henry. That's his last name. I don't remember what his first name is. But Henry has Henry's law. And Henry's law says the solubility of gas in a solution is proportional to the partial pressure of the gas above the solution. Okay, that's a lot of kind of jargony terms. What I think about it is if you have your sealed container here that's at equilibrium, you have carbon dioxide dissolved in the water, and you have carbon dioxide above the solution. So we're thinking about the pressure that's above the solution. Okay. If we rapidly decrease the volume, that increases the pressure on the top. Okay. And to normalize the system to get it back to equilibrium, more of the CO2 has to dissolve. You can think of this as literally the pressure is shoving the gas into the liquid to make it more soluble. You can also think it's in reverse. If you take the system at equilibrium and then yank the piston up, more of your gas is going to come out of solution because the pressure is lower now in the top part. Okay, that's why when you're opening sodas, you always hear it fizz. This is kind of an over-exaggerating example when it squirts out all over him. But what's happening in those cases is your soda can is in this state. Okay, and it's highly pressurized. It's probably, I forget exactly what it is. I think it's like 3 atmospheres of pressure in the top. Okay, to keep it soluble enough, right? When you open the can, suddenly it's going from 3 atmospheres to 1 atmosphere because that's what normal atmospheric pressure is. Then then the pressure is lowered and the CO2 comes out of solution, okay? And it's trapped in your can, and so it fizzes out the hole in the top of the can that you made, okay? Henry's law has a nice equation that goes with it as well. That's up here. You will be given this on the info sheet if you need it. And it just says that the solubility of whatever gas we have is related to the pressure. So this is the partial pressure above of gas above the solution. So that's P. KH is called the Henry's law constant. It's a constant, but it depends on the identity of the gas. So this is just a handful of gases. It also depends on the solvent. Okay, so it's kind of specific, but as long as you're using the same system at the same temperature and changing the pressure, the constant works okay. All right, so let's see how this would work. Let's say we have at 1 atmosphere solubility of acetylene and acetone. So this is acetylene C2H2. We don't really need to know this. And then this guy over here is acetone, C3H6O. Okay, and this is a liquid and this is a gas. So we're dissolving the acetylene in the acetone. And we know that the solubility of acetylene and acetone at 1 atmosphere is 2.7 grams per liter. And what is the solubility at 12.5? Notice we're not told what the Henry's law constant is. The nice thing is we're comparing two different scenarios. There's two ways through this problem, and I'm going to show you the easier way to do it because we're comparing two different scenarios for the same system. We don't need to know what that is. So we can think of it as saying solubility in situation 1 is equal to the constant times the pressure in situation 1, and the solubility in situation 2 is equal to the constant in pressure 2. Okay, if we take those equations and just divide them, which trust me is legal to do, what we end up noticing is, look, the constant is the same in both cases and she cancels out. So this finishes up to S1 over S2 equals P1 over P2. And we can use this because we know three other things. We know here's a pressure and there's the solubility that goes with it. And then here's another pressure. So we know both pressures and we're solving for a solubility. So when we're doing that, the best thing to do, don't get married to which conditions is 1 and which conditions is 2, right? Think about easiest to solve for S1. And this is what we're going to solve for, okay? So when we do that, we get S1 equals P1 times S2 divided by P2, okay? So S2 and P2 are the things that we know, and P1 is the pressure that goes with what we don't know, okay? So this means what? This means that we can say our solubility that we're looking for is equal to the pressure that we're looking for, 12.5 atmospheres, times the solubility that we know, 2.7 grams per liter. We can just write it like that, divided by the pressure of the 2.7, which was 1.00 atmospheres. It should be 2.70. All right. That's not too terrible, right? So this ends up being, right, 12.5 times 2.7 divided by 1. Atmospheres cancel out, and for three significant figures, we're left with 338 grams per liter is our solubility of acetylene and acetone at 12.5 atmospheres. Okay, the only thing is this is going to depend on the temperature, and so we're going to assume the temperature is the same. If the temperature is not the same, we can't do it this way. We have to figure something else out, and we're not going to have to do that. So I don't know why I said it, but there we go. Be able to do Henry's law, be able to remember the things about temperature dependence, right? Think about them in general terms and not necessarily specific examples, okay? Hope that works for you guys. I will see you in class and have a wonderful snow ice day.